So back to this question. Sorry, the previous video ran out of time. So let us go to this problem here. We have an object on a ramp. The ramp is perfectly smooth, so there is no friction. And the assumption is the object will just slide down the ramp. So we're told that the object is constrained or is going to slide down the ramp. So the only direction of acceleration is along the ramp. And I mentioned that it's a good idea to choose the acceleration, to choose a coordinate system where the acceleration only has one component. Since the acceleration is along the ramp, if I choose the x direction to be along the ramp, then my acceleration will just have an x component that's along the ramp, and then my y component will be perpendicular. There is no acceleration in that direction. I said in the earlier video that if I chose this to be the x and this to be the y, and my acceleration is like this is my acceleration along the ramp, then the acceleration will have a component along the y and a component along the x, and that just complicates the problem immensely. So this is not a good idea, right? I also mentioned that there are two forces here. There is the force of gravity because we're on Earth. The force of gravity always pulls straight down. Here is the ground, and it pulls you straight down, so it's at 90 degrees to the ground. And then there is the normal force. We know it's there because it's in contact with the ramp, and if you touch an object, it will apply a force to you, and the normal force, if the normal force wasn't present, our object would, if the ramp wasn't there, our object would just drop. But there is a ramp, so there has to be a force, and that force is normal. Normal here means perpendicular. Perpendicular to what? Perpendicular to the ramp. Always perpendicular to the object that's applying the force. So we have those two forces, and I mentioned, and then we're trying to apply Newton's second law. Newton's second law says the net force equal to the mass times acceleration, and the net force will consist of two forces, gravity and the normal force. So gravity, the normal force will have only a y component. So here is the normal force. If you like, the normal force does not have an x component. It does not have an x component with this choice of axes. It only has a y component. The normal force y component is just n. It's just the normal force. The force of gravity has two components because the force of gravity is not perpendicular to this x direction, and it's not parallel to the y direction, so it has actually two components. So here is my mg. I want to break this mg, this vector, to have a component along the x and a component along the y. It's actually along the negative y direction. So I know this is 90 degrees and this is a triangle, and the sum of the angles of a triangle will be 180. This is 90 already, so these two have to add up to another 90 to make up a 180. So if this is 90 and these two have to add up to a 90, then if this is theta, then this has to be 90 minus theta. But this is a 90-degree angle. So this and this have to add up to 90. So whatever this one is, it has to be theta. Because theta plus 90 minus theta will give me 90. So this angle here is actually theta. This angle here is theta. All right. So I will, so from now on, you can use this to be theta. All right. So what are the components of the force of gravity? Well, the force of gravity will have a component along the x direction. So the force of gravity, x component, will be the force of gravity times the cosine of the angle that the force of gravity makes with the x-axis. You can use this angle here, or you can say it's the sine of this angle. Whatever you prefer, it will end up being the sine of this angle. So let me use this angle. So here's the positive x-axis. This is below the x-axis. So it will be cosine of that angle it makes with the x-axis. And since it's below the x-axis, it will be the negative of this angle here because it's below. If this is 30 degrees, it's negative 30 degrees. So it will be negative of that. So it will be theta minus 90 degrees. And you can verify using trigonometry that the cosine of theta minus 90 degrees will be the sine of theta. Would be the sine of theta. So it is just FG, F, the force of gravity times the sine of theta, and the force of gravity is mg, so it's just mg sine of theta. I know I'm doing this in great detail because you probably have seen it and have seen enough of it, but I want to just make sure that we fully understand it. How about the y component, the force of gravity? Y component, I mean, it's the adjacent to this and it's negative, so it's just mg times the, since it's the adjacent, so it would be mg cosine theta with a negative sign, so it's minus mg sine theta, mg cosine theta. But let's see how it comes out from this. So it would be the force of gravity times the sine of the angle it makes with the x-axis. And that angle is theta minus 90 degrees, theta minus 90 degrees. And the sine of theta minus 90 degrees is equal to the negative cosine of theta. So it would be minus fg times the cosine of theta. So that's minus mg cosine of theta. Minus mg cosine theta. And so let me show you how we can do this, and how we can do it also in vector form. So let me just show you how you do that, to be as detailed as possible. We will start skipping details afterwards. Okay, so we say, by Newton's second law, the net force in the y direction, I'll start with the y. It doesn't matter where you start, but I'll just start at the y, will equal to the mass times the acceleration in the y direction. By this choice of axis, we just said that the acceleration in the y direction is 0. There is no motion perpendicular to the incline. There is only parallel to the incline. And the acceleration in the x direction, we'll just call it a. It's a. So this side here is 0. So I know that the right-hand side is 0. What are the forces in the y direction? Well, you get the normal force, the y component of the normal force, which I'm calling n. And then, plus the force of gravity in the y direction, the y component of the force of gravity, but that's negative mg cosine theta minus mg cosine theta. So this will give me that the normal force is mg cosine theta. That's that. Okay. All right. And then the net force in the x direction, the net force in the x direction would be, it would be what? Would be the mass times the acceleration in the x direction. So mass times acceleration in the x direction, just call it ma, because the acceleration in the x direction, we agreed to just call it a. There is no y component. What are the forces in the x direction? The only two forces we have are the force of gravity and the normal force. So the normal force, the component of the normal force in the x direction is 0. I can write it this way. The normal force, the x component of the normal force, plus the x component of the force of gravity will equal to ma, But the x component of the normal force is 0. It has no x component. The force of gravity has an x component of mg sine theta. So I have here mg sine theta equal to ma. The mass cancels, and I just have the acceleration will equal to g times the sine of theta. Okay, that's it. And you probably have seen this result, and now you can do it a lot quicker than we did. So I just want to show you how you write things in vector form. So we said that the net force will equal to the mass times the acceleration. The net force consists of the normal force and then the force of gravity equal to the mass times the acceleration. The normal force, let me do it here quickly. Normal force would be the x component of the normal force I hat plus the y component of the normal force j hat. And And so the normal force, this is 0, so it's just equal to the normal force, the y component, which you call just n. The x component is 0, so it's just n j hat. And the force of gravity will be the x component of the force of gravity I hat plus the y component of the force of gravity j hat. And so that means the force of gravity will be what? The force of gravity in the x direction is what? What did we say? It is mg sine theta. Mg sine theta I hat. And then the force of gravity in the y direction is negative mg cosine theta. So I put minus mg cosine theta j hat. Okay. How about the acceleration? The acceleration is the x component of acceleration I hat plus the y component of acceleration j hat. But acceleration does not have any y component, that's 0. And the x component of acceleration, we agreed to call it a, so it's just a I hat. So let's write them down here. The normal force is n j hat, so it's n j hat. The force of gravity will be what? Is mg sine theta I hat plus mg sine theta I hat, and then minus mg cosine theta j hat, that's for the force of gravity, equals to the mass times acceleration, but the acceleration is just a I hat times m. So it's the mass times a I hat. You can set the I hat components, the x components equal to each other, and the y components equal to each other. So the normal force j hat minus mg cosine theta j hat, there is no j hat on the right side, so that means it's equal to 0. So it means that the normal force, if you take this to the other side, will equal to mg cosine theta, which we got, mg cosine theta here. And then the I hat parts get equated to each other. So this part get equated, the mass cancels. So, and then you get g sine theta for the acceleration in the x direction. So when you have a vector formula, a vector equation, it's really multiple equations. So if you're in 2 dimensions, it's 2 equations hidden in there because you have I hat and j hat, and you equate the I hat parts to the to the I hat and the j hat parts to the j hat. If it's a 3 dimension, it would be it's 3 equations with that you need to solve. All right, so that is that, and I now want to talk about friction. So I was going to start to talk about friction, but since friction is talked about in chapter 6, why not start chapter 6, which is the applications of, which is called Dynamics 1, Motion Along a Line. So let me write it down, write the title, and it's really just a set of examples. Chapter 6, Dynamics 1, and I think it's motion along a line. Okay, yeah, motion along a line. Motion along a line. Okay, sounds good. And so let's just start with it. So let's say you have a car, example. So we're going to basically put all the forces together and just apply Newton's laws. So here is a car, and the car is being towed. So let's say it's being towed along a ramp, and it's being pulled this way, right? So here is the car, and the car has a mass m, and let's say the ramp is of theta. Here, the angle is theta. And it's being pulled. Let's call this the force of tension because it's being tied. there is a tow truck, and the tow truck is pulling on the car. The effect is that there is the force of tension on the car. And let's say the weight of the car. By the way, the weight is mg. The mass times gravity is known as the weight. And let's say our car is, let's just, I think it's 16,000 newtons or so. 15,000 newtons. 15,000. Yeah, the car is 15,000 newtons. So it's being moved upward at 15,000 newtons. And and we're also given that the car is moving at constant speed. In fact, it's constant speed along a line, so it's constant velocity. So you know right away, if it's a constant velocity, it means the acceleration is zero. If the acceleration is zero, Newton's first law says the net force has to be zero, if and only if, right? You have constant velocity if and only if the net force is zero. So it means whatever the forces here are, they will add up to zero. What are they? Well, we're told it's being pulled with some rope, with something. There is a tension here. And the question is, find the tension, by the way. The question is, what tension is needed to make this happen? And the angle, I think, is 15 or 20 degrees. I can't remember at the moment. 20 degrees. The angle is 20 degrees. So what are the forces? How do I know there is tension? Because I'm told there is a rope being pulling it. And then what else? There is the force of gravity, and it's straight down. The force of gravity, it's mg. And that mg is 15,000. I will just work with simples for now. And then it's on an incline, and so it's touching an incline, so there has to be a normal force, and the normal force is this way. It's at 90-degree angle. And we said, let us choose our coordinates to be, to have this to be the x direction, and this to be the y direction. And remember from the previous problem that we did, we said if this is theta, then this angle is theta. And so let me write it this way. So the normal force, the x component of the normal force will be zero. The normal force does not have any component along the incline. It only has a y component. The normal force, the y component is just m. The mg, the force of gravity, they use capital G. The x component of force of gravity will be this way. So it's in this negative direction. So it's the opposite here. If you can look at it from earlier. So this is the positive x direction. It's opposite to it. So it's negative mg sine theta. The y component of the force of gravity, it's this way, and it's adjacent to theta here. So it's mg cosine theta with a minus sign. We did this in more detail in the previous problem. Please refer to it. So these are the forces involved, and then we have one more, the tension. The tension force, the x component is just T. The y component of tension is simply zero, because the tension is pointing in this direction. So it's, if you like, it's T cosine theta, but the angle is along the incline, so it's 0 degrees. And then, I'm sorry, T cosine for x, so it's at 0 degrees, so it's just T. And the y one would be T cosine, T sine, and the sine of 0 degrees would be 0. So those are the forces. There is no acceleration. The x component of acceleration is 0, and the y component of acceleration is 0. So we write Newton's second law, or first law. The net force is 0, so the net force in the x direction, we said it's 0, because there is no acceleration. In the x direction, I have the x component of the normal force, plus the x component of the force of gravity, plus the x component of the tension. They have to add up to 0. The x component of the normal force is 0. The x component of the force of gravity is minus mg cosine theta. It's minus mg cosine and our Tx here is just T plus T equals to 0. So move this to the other side, so you have the tension will just be mg cosine theta. Mg is 15,000, so it's 15,000 newtons times the cosine of, what did I do? Mg times the sine, I'm sorry, it should be sine. The sine should be the sine of theta times the sine of 20 degrees. And so the tension is simply, let me just look it up in my calculator here. You have about 5,100 newtons, 5,100 newtons. Actually, the book says, will the cable break? They say the cable has a rating of 6,000 newtons. So this cable, if you apply more than 6,000 newtons, it will snap, it will break. And so you're applying 5,100 newtons, so it's fine. It's fine. It's still well below that. Okay, looks good. So let us continue. All right, so one more tow track problem here. So a 1,500 kilogram is being pulled by a tow truck. The tension in the rope is 2,500 newtons, and a 200 Newton friction force opposes the motion. And then it says if the car that's being towed starts from rest, what is its speed after 5 seconds? So we're assuming here they didn't say it's an incline, so it would just be, let me get my red pen. Here it is. So I'll put a solution here. I have to draw something. We have to draw a little picture here to figure out what's going on. So it's horizontal here. Here is our car, nothing fancy, just a block for the car. And you ask, what are the forces? Let's assume the car, I like the right, so the car is being towed this way, so the tension is this way. You could equivalently say it's being towed that way, so the tension would be this way. That's fine. I'm assuming it's being towed that way. It's arbitrary. Okay. What are the forces involved? Well, there is the force of tension. The car is on Earth, so there is the force of gravity. And then the car is on a surface, it's in contact with the surface, so there is the normal force. And then they said there is 200 newtons of friction that opposes the motion. So if the motion is to the right, there will be friction to the left. I know we haven't talked about friction, but they're telling us how much is that friction and in what direction. So they're just saying there is a force of friction this way. I'll just call it force of friction. And it's 200 newtons and it's this way. Maybe the arrow should be a little shorter because this is 2,500 and this one is just 200 to the left. That's it. Those are the forces. So those are the forces. Now we have to draw our coordinates. So in this case, it's easy. The motion is along the x-axis. So I'm going to say, all right, here is the x and here is the y. So our object will move along this way. So there is no acceleration in the y direction, but there is acceleration in the x direction. So the acceleration in the x direction, let's just call it a, and the acceleration in the y direction is simply 0. The car is not being lifted and it's not going into the ground. It's only moving this way. That's the assumption of the problem, we're told. Okay, so let's figure out. So first of all, the x component of tension, well, tension is entirely in the x direction, so that's 2,500 newtons. The y component of tension is 0. Tension, in this case, it's being pulled horizontally. There is no y component. The x component of friction, the force of friction, it's to the left. It's 200, so it's negative 200 because it's to the left. The y component of friction is simply 0. Friction is just opposing the motion. If the motion is to the right, friction is to the left. It doesn't have a y component. It's not like in this direction, just that way. Okay? Now, the the force of gravity, the x component is 0. Force of gravity is pulling you straight down. Gravity is not this way or this way. it's just straight down, and it is equal to mg. The y component of gravity is minus mg because it's in the negative y direction. How about for the normal force? The x component of the normal force is 0, and the y component of the normal force, well, let's just call it n. I don't know what it is, it's just n. They didn't ask for it. What we care about here is the motion along the x direction, so I will ignore the y direction. I will ignore it until maybe we need it, okay? If we don't need it, then we don't need it. So we just apply Newton's second law in the x direction. Newton's second law in the x direction, it says the net force, or the sum of the forces in the x direction, will equal to the mass times the acceleration in the x direction. All right, what are the forces in the x direction? There is the x component of tension and the x component of friction. The normal force and gravity, they have 0 components in the x direction. So you just have, if you like, you can write all the forces. You can say the x component of tension plus the x component of friction plus the x component of gravity plus the x component of the normal force equal to the mass times acceleration in the x direction, which we agreed to just call it simply A. So again, gravity doesn't have an x component and friction doesn't have an x component. So we could have just not even written that. But this is just to be explicit. The x component of our frictional force and the tension, this one is 2500 and this one is negative 200 for friction. The mass of the car is 1500 kilograms times the acceleration, should say. 2500 minus 200 is 2300 equals to 1500 A. Get rid of that. And so the acceleration will be, I will need a calculator, give me one moment, will be 23 over 15. So that's 23 divided by 15. I get 1.53 approximately, 1.53 meters per second squared. And so that's the acceleration. So once you find the acceleration, now you can go back and use kinematics. It says if the car starts from rest, what is the speed of the car after 5 seconds? Well, I know that motion at constant acceleration here. The acceleration is constant because the forces are constant. You got the velocity here, the x component of velocity, obviously, because there is no motion in the y direction, will equal to the initial velocity plus the acceleration times the time, or initial here. I can put initial. So the velocity would be, initial velocity was 0, it started from rest. This one is 1.53 for the acceleration. And times the time, which is how many seconds again? 5 seconds. And so velocity later will be 7.6666 repeating. So 7.67, let's say. 7.67 is good enough. I think they want 2 sig figures, maybe 7.7. Again, as far as significant figures, I don't care. Keep as many as needed. If you keep an extra one, don't worry about it too much. Don't let the significant figures prevent you from learning the physics itself. Don't worry about that. So my attitude is about significant figures is keep as many as you need to, and then you can always get rid of the digits to make your instructors happy. All right, good. And again, I think our book says assume there are 3 significant figures in every problem. I would say when I assign an exam problem, just even if I don't explicitly write it, assume it's 4 significant figures. Everything is now into 4 significant figures, maybe 5 if you want. So anyways, what we care about is really this, okay? That's the one. All right, so let me make sure that we have everything good. Yes, everything is correct. So we will. So we're in. By the way, again, we're in chapter 6. So let us look at the next problem. So we will go to the next video to do the next problem.